So today we'll start where we were left off in the last class. So in the last class we were introduced the BJT, right? So like if I will show you, so last class we have seen how in a BJT the current transfer takes place from emitter by junction to collector by junction, right? So the true criteria that we have seen is for efficient transfer, right? So the two criteria are the doping in the emitter region should be very, very greater than the doping in the base region. The second criteria is base width should be very, very small compared to the diffusion length. So that whatever carriers will be injected from emitter to base, that will be passing to the collector without having much of a recombination, right? This is the criteria. And this NE should be very, very more in order to increase the emitter efficiency. What the emitter efficiency? So the amount of carrier injected across the emitter junction will be, most of them will go to the collector, right? So this is the two important criteria for a proper transistor action. That is a transfer of current from emitter base junction to the collector junction. Then we have introduced something called emitter injection efficiency, nothing but current from base to emitter, emitter to base by total current. Like emitter injection efficiency is nothing but here in this picture, if you see, yeah. So whatever currents have been injected from emitter to base divided by total current, that is IEN divided by IEN plus IEP. See, the IEP is the current injected from emitter to base. So IEP divided by IEP plus IEN is the injector efficiency. And base transfer factor is the current that is transferred to collector and the current that is injected into the base. Okay. So that we have seen there is something called alpha. Okay. Alpha is nothing but ICB by IE. Then we have seen alpha is nothing but emitter injector efficiency into the base transfer factor. Okay. So in this class, we will see qualitatively, right? The alpha, how to derive a alpha, that we will see in this class. Okay. So there is something also called beta, B, nothing but the collector current by base current. We have seen, we have derived it is alpha by 1 minus alpha. So also we have seen what is the effect of collector bias. So when you forward bias, you have seen it is destroying my transduction because the slope of the carrier in the base is reducing. So the current which depend upon the gradient is reducing. Also, since electrons have been injected in the same direction as the hole, so the total current, you see, total current is ICP minus ICN. ICN is nothing but current due to the injection of electron from base to collector, and ICP is the current due to the diffusion gradient, concentration gradient. Okay, so if you see, when we apply forward bias, it is destroying my tight traction because the current is decreasing. Okay. Then you've seen in reverse bias, the current is the transduction is taking place properly. Only thing is, instead of if you have a common emitter configuration, IC is equal to alpha I if the base to collector junction is not reverse bias. If it is reverse bias, there is a reverse saturation current that is coming into picture. That's all. So instead of alpha I plus there is small reverse saturation current that is coming into picture. Okay. So also we have seen the flow diagram how it is takes place. Then we will start something build small signal analysis of a BJT. Right? What is the meaning of this? Suppose I have taken a BJT. Okay. So this is my yes. Okay. So this is my emitter. This is my emitter base collector. Okay. So there is a depletion region nearby. You know, all of you, this is a depletion region. Okay, this is a depletion region. Okay, so here the depletion region. This is the depletion region. Okay, so what we have seen, if we apply a emitter to base product wise, suppose this is P plus N P, P and P transistor. Okay, P plus N plus P. Okay, this is the doping concentration. So if you apply a product wise to the base to emitter junction, okay, even if my collector to base junction is zero bias, there is a current flows, right? Nothing but transistor action. So if I apply a EB, there is going to be a current that is called emitter current, nothing but my base current, base current. So this is nothing but my collector current. Okay. So what I'm asking small signal means, suppose I change my emitter to base bias a little bit, very small. Okay, maybe change by a little bit. I give a small increment in dB. Okay, then definitely, since my emitter to base bias is changed, there will be a change in emitter current. Right, small change in emitter current. Right, and also there should be a change in base current, and there is change in collector current. C plus del IC. So if you change the emitter to base junction by a little amount, there will be change in current in the emitter, base and collector. Right. So how the amplification takes place, right? So the first step is to relate what is the change in collector current if there is change in emitter base voltage. So if you can establish a relationship between change in input base to emitter voltage to change in collector current, okay, so we can know how the amplification takes place. So the first step is to relate del IC to del VEB. So for that, first thing is we know IC is equal to alpha into I. So del IC should be alpha into del I. Right? So change in collector current is alpha times the change in emitter current. So for that, we will first derive a expression for emitter current using the theory from PN junction. Right? So we know in a, so suppose this is my base junction. Okay. This is my emitter, this is my base, this is my collector. Okay. Since emitter to base is forward bias, we know there will be injection of hole from emitter to base. So this is my hole concentration like this. There will be injection of electron from base to emitter. This is my, okay. So this quantity del P, quantity is del Ne. It is del, okay, this quantity del Ne. So in order to derive the emitter current, we need to know the concentration profile, right? Like we have seen in diode. Okay. Then we know what is del P. Del P is same as what you derived in the PN junction theory. Del P is the concentration of holes at the edge of depletion region, right? In the base side, nothing but depend upon my emitter to base voltage, right? So it is equal to how much it was there already, increased by exponential of VB by VT minus 1, right? This is my del P. Similarly, del N is in the same way, again depending upon the base emitter voltage, how much it was there already, NP0 is a magnetic carrier in the emitter region, right? Where this is P plus plus N plus this is N, right? So into exponential of PV by VT minus 1, right? So this is the concentration at the edge of the represent region in base and emitter. Okay, so also the emitter current will be sum of this current plus this current, right? So this current will depend upon the concentration gradient. Also this current will depend upon the concentration gradient. So like we have derived in the P junction theory, so the emitter current will be equal to the area of the emitter into the charge into what is this current? This current will be nothing but Q dp by dx, right? So depending upon the concentration gradient, so equal to dB. dB means diffusion of magnetic area in the base region. This is the diffusion constant of the magnetic area in the base region, Q dB into dp by dx. What is dp by dx? dp by dx is del P by what is dx? dx is nothing but base width. This is nothing but your base width. Okay, so in P junction theory, it was WB replaced by LB, diffusion length. But here, since the base width is very, very small compared to diffusion length, we have to replace with base width. Okay, plus diffusion constant of magnetic area in emitter region into del Ne divided by LP. LE, the diffusion length in the emitter region. Okay, this is my current, right? Q dB by dx. This is a simple diffusion current. Okay, so we know, so A into Q. We know del P dB into what is del P? Del P already I derived Pn0 into this. So Pn0 by WB plus D into N P0 by LE. So this will be coming outside. This exponential factor will be exponential of VB by VT, not VB, VEB. VT minus 1. Okay? So this is the current of emitter region. Okay, so this thing you can denote as a reverse saturation current IE0, like we have denoted ID0 into potential of by VT minus 1. Okay, this is my current. So I have derived because we understood the P junction theory very well. Okay, now if you do the derivative, right? So what will be the del IB? So if there is change in this, so since I'm ignoring this minus 1, okay, because exponential term is very, very more compared to 1, so I can ignore this one. So now if there is change in VEB, IE plus del I is equal to IE0 into exponential of VEB is changed by a little amount del VEB. Okay, so this is my total current when my base to emitter to base voltage changed by a little amount, right? This is my total current. So now we know IE0 into exponential of VEB by VT into exponential of del VEB by VT. Okay, so equal to this term is nothing but your current I, right? This is my I. Since del VEB is very, very small compared to the, so assuming del VEB very, very small compared to VT, because I am increasing the emitter to base voltage just little amount. Okay, so assuming this condition is true, so the exponential can be replaced by using Taylor series 1 plus LBEB by VT. So this implies I plus del I equal to I plus I into del VEB by VT. So this I will cancel. What is del I? So the change in current because of change in emitter to base voltage equal to I by VT into del VEB. So if this condition is true, like I am changing the emitter to base voltage by little amount. In that case, the change in emitter current will be directly proportional to the change in emitter to base voltage, and it will depend upon at what current you are. Okay, this I is nothing but I is the current before application of the increment. Before the application of the increment, what is the current I? Is nothing but your, in terms of your amplification, in terms of amplifier terminology, this is called quotient current. Quotient current is nothing but the current that is flowing in the transistor before the application of small signal. So the change in current will depend upon my I, nothing but this is called quotient current. UE, quotient or DC current, I can say. Okay. So this is the current that is flowing before the application of the a small signal. Okay. So the change in current will depend upon the quotient point where the transistor is operating before the application of the signal. Okay. So this is by change in IB. So now I want a change in collector current equal to alpha into del I equal to alpha into I by VT into del VEB. Okay. So this term is called as transconductor GM into del VEB, del IC. So del IC is related linearly to the change in emitter to base voltage as long as the change is very small. As long as the change is very, very small, del IC is GM into del VEB. GM is nothing but your transconductance. Okay. So the change in collector current is directly proportional to the change in base emitter voltage as long as it is small, and the constant proportional is called transconductance GM. Okay. So now if this change in current will pass through a resistor, right? So in this, suppose it will pass through a resistor. Here, suppose it will pass through a resistor. Suppose it will be resistor R, right? What is the voltage at the output? Output voltage will be change in output voltage will be del IC into R equal to GM into del VEB into R. So this is the change in output. This is the change in input, right? So the change in output by change in input equal to GM into R. So the output signal is GM into R times the input signal. So this is nothing but your amplification factor. Okay, this is nothing but your amplification factor. Okay. So the output signal is GM into R times the input signal. So which is nothing but amplified version of your input signal. Okay, so for the which we depend upon GM. Okay, so the amplification factor depend upon GM and R also. Okay, and GM depend upon the IE. So IE is nothing but your constant operating point. So this is called operating point. So before the application of signal, at what point you are. Okay, this is IE. So this is your amplification factor. So more on this we will talk very detailedly in analog circuits. Okay, this is just to give you a understanding of how amplification takes place. So one more thing. So since this, the voltage here is positive negative like this. Okay, this is nothing but V0 plus del V0. So this may forward the transistor. So when it is forward, right? See, this is P is positive, N is negative, right? Then the collector base junction is forward, then the transistor action base will not take place. Right? For the transistor action to take place, the base to collector junction should be zero bias or reverse bias. So when you connect a resistor like this, right? For signal and output, you see, this is positive, this is negative. This may forward bias the base to collector junction. So there should be a bias BCC in the reverse direction. So this the bias voltage such that for all the signal and the question operating point, it will ensure the BCC plus this voltage is negative, so that the base to collector junction is reverse bias. Okay, this is the use of this BCC. Okay, so this will ensure that in the entire execution of the signal and the operating point, this will never forward bias the collector base junction, so it won't disturb the transistor axle. Okay, so this is the thing. So now we will see what is the effect of reverse bias on the. So we will see the effect of reverse bias. Reverse bias in B junction. Okay. So first thing is there are two main effects. The first effect is we know IC is equal to, right, alpha I plus ICO, right? So because of reverse bias, a temperature changes, right? This ICO will change. Okay. So if the ICO will change, then definitely the collector current also will change. Okay. Then since my GM is equal to alpha IC by VT. Okay. So since IC is changing with respect to temperature, GM will change because IC is changing. So since GM will change, also the amplification factor will change. So the amplification factor will not be constant. Okay. So that is the issue. So the ICO will cause the change in the amplification factor, nothing but change in the operating point. Okay. This is the first issue. Second issue, second not issue, is called base width modulation. Okay. So this thing already we discussed earlier, right? So when we reverse bias, right, this junction will, this diffraction width will widen. So this diffraction width will widen because when you increase the reverse bias, the diffraction width in the base to collector junction will be widened. So it will shift like this, like this. When it will shift, okay, the concentration gradient will be like this. So if you see the concentration gradient is increased. So then my base width will decrease because of the expansion of depletion width due to reverse bias. It will increase the concentration gradient in the base region. So since the collector current depend upon my concentration gradient, so it also will increase. So there is nothing but your base width modulation. So the increase in collector current due to change in or decrease in base width because of increase in reverse bias in the base to collector junction. I am repeating, the increase in collector current due to increase in depletion width or decrease in base width because of increase in the reverse bias base to collector junction. Using terms, increase the slope of the carrier, so the collector current is increasing. There is nothing but your base width modulation. Okay. So in order to know how if I decrease the base width, how if I decrease the base width, this is nothing but your base width. Okay, this is base width. How if the base width is decreased, why the current will increase? We have understood qualitatively. Also, in order to understand mathematically, we have to derive an expression for the current gain alpha. We will see then base width will decrease, my alpha will increase, so that my current gain, nothing but collector current will increase. So we have seen the base width modulation is affecting your collector current. So qualitatively we have seen. So we have seen in qualitatively how it happens. But in order to see quantitatively, we will have to derive expression for alpha. Okay. So first we will derive expression for alpha. Expression for alpha. Okay. So alpha we know equal to the emitter injection efficiency into the base transport factor. Right. So we know the emitter injection efficiency is equal to 1 plus IEP, current due to injection of holes from emitter to base, by IEN, current due to injection of electron from base to emitter. This is my emitter injection efficiency into what is base transfer factor is nothing but 1 minus recombination current divided by the current injected into the emitter, IEP. Okay, this thing you know, already discussed. Okay, so now we'll derive a expression for IEN by IEP. It's actually mistake here. Is IEN by IEP. So IEN is the current injected from base to emitter. IEP is the current injected from emitter to base. This is whole current. This is in a PNP. This is a whole current. This is a electron current. Okay. So now, what is IEN by IEP? IEN by IEP. So we know in base emitter junction, emitter base junction, right? So when we apply forward bias, okay, this is my collector junction. So you see the profile of the carriers is like this. Okay, so this is del P, this is del N E. Okay, so IEN, you know, IEN is U del Ne U D. D is the diffusion constant in emitter region due to magnetic carrier into U diffusion constant into del Ne divided by Le. Diffusion length in the emitter region. Okay, this is my IE. What is IEP? IEP is Q into diffusion constant in base region into del P by base width WB. Okay. So this implies Q get cancelled. Okay. So what we got? D, which in below D will get dB. Above we got double B, below we got LE. We know del NE is nothing but Ni square by doping in emitter region. So Ni square by doping in emitter region is Ne. Finally, what is del P? Del P is Ni square by doping in base region Nb. Right? So this will cancel. So what will get? We will get Nb into d into double B divided by Ne into dB into Le. This is my IEN by IEP. So this thing is very clear, right? If you understood the brain junction theory. So, what is the recombination current by the IEP? We know the recombination current depend upon the how much charge loss in the base region, right? So charge loss is depend upon your the area under this curve, right? So this is Q into half. If I approximate this is a triangle, half into LP into double B. This is the area under this curve, okay? Into A, right? A should be there. Here also should be AE by AE. Okay. This is the total charge. Okay. This total charge lost in how much time? In the tau B. Tau B is the magnetic area lifetime in the base region. Okay. So this is the charge is getting lost in tau B magnetic area lifetime. Nothing but your recombination current. Recombination current is charge divided by the time. Time is the magnetic area lifetime. And this is the charge lost in that direction. Okay. This is my IR. What is IP? IEP, you already know is this one, right? So IEP is Q del P into D into A Q dp into double B, right? Into double B. Because Q del P D A by double B. Okay, this is the IEP, we know. Because Q D dp by dx. Dp by dx is del P by double B. A is the area of the emitter. Okay, Q D del P by del x. Del P is del P by base width. This is the slope of the carrier. Okay, this is your IEP. Then what you will get? You see this AQ get cancelled. AE get cancelled. Okay, so del P get cancelled. So what is remaining? So what is remaining is half. Okay, W square dB. This is dB. Okay, because this is the diffusion in base region, right? Base region. It should be diffusion content in the base region. Okay, dB. So we got half WB into WB is WB square by tau B into dB. Okay, so we know tau B into dB is nothing but diffusion constant, diffusion length square. So equal to half WB square by LB square. This is IR by IEP. Okay, so using this information, now we'll put in this equation alpha. So what is alpha now? Alpha is equal to 1 by 1 plus IEN by IEP. IEN by IEP is this one equal to NB into 3 into double B divided by NE into dB into LE into 1 minus IR by IP, 1 minus WB square by 2 will be square. Okay? This is alpha. So you can see very clearly when VCB reverse bias is increased, then base width is decreasing. Since base width is decreasing, we know this factor will decrease, but if it will increase, this factor will decrease, also this factor will decrease. So alpha will decrease. So you see mathematically, when you change the collector to base junction, reverse bias, it is decreasing my base width. We have seen qualitatively it is increasing the concentration gradient, and also it is sorry. What is happening? Just a minute. If you increase the collider to base junction, okay, the depreciation width will increase. This will increase, but the base width will decrease. Okay, base width will decrease because when you increase VCB, the depreciation width will increase, but the effective base width will decrease. When base width will decrease, we know if it will decrease, then this factor will increase. If it will decrease, then this factor will also increase. So both will increase. That means alpha will increase. So since my current gain alpha is increasing, so my collector current also will increase, because collector current is IE, IC is equal to alpha into IE. So since alpha is increasing, so my IC also will increase, right? So that is why mathematically or quantitatively we can prove that if my base width is decreasing because of collider to base reverse bias increasing, so my alpha also is increases, so my collector current also increases. This is nothing but your base width modulation. Okay, this completes your discussion of this base width modulation. So one thing is remaining on this one. So till now what we were discussing is this one. So what we were discussing till now, we have taken a PNP transistor. We have given the input forward bias, okay, and we try to give this reverse bias. Okay, here if you see, this is emitter, this is base, this is collector. Okay, and here the emitter to base junction is biased with respect to base. The base to collector junction also is biased with respect to base. This is your common base configuration. Okay, so this is your emitter current I. Okay, this is your IB. This is your IC. Okay, so if a BJT is biased with respect to base, okay, then it is called common base configuration. There is another configuration called common emitter. Okay, where BJT will be biased with respect to the emitter as common. This is emitter, base, collector, PNP transistor. Okay, so what we will do, where will bias with respect to emitter. So where emitter will be common. Okay, so we'll bias PNP, you have to bias the emitter. Even this also will be biased with respect to emitter. So for signal, we have to put a resistor here. We have to put a resistor here. So here the collector to base junction is biased with respect to emitter. Okay, so this is emitter is common to input. This is input. This is your output. Okay, so here base is common to input and output. Here emitter is common to input and output. That's what is called common emitter configuration. Okay, so in common emitter configuration, okay, what is the input current? Here the input current is IB. Here, right? Sorry, here the input current is IE, right? This is the output current IC. Okay, so here IC is equal to alpha into IE. But here the input current is IB, the output current is IC. So here IC is equal to beta into IB. Okay, this is the condition. Okay, so in common emitter configuration, the output current is the beta into the current gain. Beta current gain is beta into IB. So beta is always greater than 1. In common base configuration, the alpha into I, alpha is less than 1. Okay, so this is the common emitter configuration, which is very much popular, right? Compared to common base configuration. So only thing is you have to bias in a different way, and it will change all the characteristics of the amplifier. So this biasing configuration we will see in analog circuits will change all the configuration, like everything, bandwidth, input resistance, output resistance, gain, most importantly gain, everything will change. Okay, so the bandwidth of this will be different, this will be different, the gain for this will be different, this will be different, so everything is changed. Okay, so these things will be discussed very detailedly in analog circuits. So the common emitters configuration is very much useful in amplification application. Okay, so one thing, since we know we derived alpha I plus ICO, right? So this is we have derived in CB configuration. So then what is the relationship in CE configuration, right? Because this IC is nothing but your reverse saturation current. Reverse saturation current. Okay. Correct. Okay. So now how to derive in terms of IB? Because in common emitter configuration, the input current is IB, right? So how to derive that? So equal to, so simplest IC equal to, what is I? I is nothing but your IC plus IB plus ICU. IC into 1 minus alpha equal to alpha into IB plus ICU. Simplest IC is equal to by 1 minus alpha into beta plus 1 by 1 minus alpha into ICU. Okay, so this is nothing but your beta. Beta is current gain of common emitter configuration to IB plus this is equal to 1 plus beta into ICU. ICU is equal to this equation is for common emitter configuration. This 1 plus beta is also you can write ICU. Okay, this is, since it is in common base configuration, I can write ICBU. So ICU is equal to 1 plus beta times ICBU. This is very important for exam. Okay, so this is just a simple equations you can easily understand. Okay, so next we will discuss last thing in this chapter, last but not the least. Okay, so what is this? We will discuss now. We will discuss okay. So last thing remaining we need to cover this in this lecture is how to derive the output characteristic of the common. So the output characteristic of common emitter configuration. This is my last thing you have to understand in BJT. Okay, so if you, so this is very general. So if you understand how to derive for common emitter configuration, similarly you can derive for any configuration, right? So let us now discuss. So we know in a BJT, right? The NP transistor, right? So we know if for a common emitter junction, right? If suppose my input current IB is constant, right? If I vary VEC, VEC, we will see the characteristic like this. So if I want to plot the collector current IC, so IC versus if I want to draw VEC. Okay, so I want to plot the magnitude of IC versus VEC. Okay, by maintaining my input current IB constant. Okay, nothing but I can say input bias also. If you make the bias constant, the current will be constant. So in other way, I can say my input current is constant. Okay, so if you change the emitter to base voltage, you will see the current will be like this. Okay. Okay. This is my output characteristic for a particular IB is equal to constant, right? So how this characteristic have come, that we will discuss. Suppose if I change IB1, suppose I will increase my IB2. Suppose I will go to IB2. So suppose if I go to IB2, it will be like this. This is for IB2 greater than IB1. Okay. Suppose I go to another IB3. This is for IB3 less than IB1. Okay. So there are various curves we are getting for different base current. Okay, so how we are getting this IB characteristic and how it is very useful for your amplification process, that we will understand. Okay, so first we will start from base is equal to 0. Okay, so let us first concentrate on only one curve. You see, in a PNP transistor, right? So the electrons will be emitted like this. Sorry, the holes will be coming like this. So the collector will be out of the collector, right? The current will be out of the collector because you know the if you see the this is my hole profile, then the current will be like this. Current will be coming out of the collector. Okay. So first thing we will discuss is what will happen when V is equal to 0. 0. Right? So VC is nothing but VB minus VCB. Okay. So VC is equal to 0 is this implies VB minus VCB is equal to 0. Right? VB equal to VCB. Correct? So what is the meaning of this one? Okay. So emitter to base junction bias is VEB, VCB, VC, VCB. Okay. So when VEB is equal to VCB, okay, what will happen? That we will see. First point is VC is equal to 0, VEB is equal to VCB. VCB. Okay. So first let us draw the concentration profile in the. So you know this base, this is emitter, base, collector. Okay. We know the concentration at the edge of the depletion region, okay, is depend upon the bias in the junction, right? Since the emitter to base junction is same as collector to base junction, the concentration, suppose this is P, N, this is P, okay? So since VEB is VCB and both junctions are forward bias, right? Both junctions are forward bias, okay? VEB is equal to VCB and both are forward bias. So the holes will be injected from emitter to base and the holes will be injected from collector to base, right? Both are forward base, and also the electron will be injected from to emitter and to collector, right? So electron will be injected from base to emitter, base to collector. Holes will be injected from emitter to base and collector to base, right? You see. So since here you see this is very more, the doping is very more than base, then collector, right? So the collector is lightly doped compared to base and emitter, okay? And so if first we will plot the concentration profile in collector, okay? So in collector, the electrons will be, right, injected from base to emitter. So if you want to draw the profile, it will be like this. Okay. So this is del NC, the excess electron concentration in collector region which have been injected from base to collector, okay? And now I want to draw the profile in the base region, okay? You see, suppose you will assume that the base region is almost 10 times heavily doped compared to collector region. So here you see, it depends upon the doping rate. So here this is proportional to Ni square by proportional to N square by n doping. Here doping is very less, so it is very high. Since it is very more, so it will be little less than 10 times less than. So if I assume that doping in the base region is 10 times more compared to doping in collector region, so it will be little less. And you see, since both the junctions are same bias, so the value of the excess carrier at the junction and at the junction will be same. Okay, so it will be like this. Okay, this is my, because the excess carrier at the junction will be equal to excess carrier in the collector base junction, because both are having same bias. So this will be my profile in the base region. Okay, and in emitter region again it will be less because it is very heavily doped. It will be less, very less. This is nothing but your del N E. This is del P B. Okay. So now you see how the current have been flowing. Okay. So the first thing is you see the electrons have been injected into the base. So the electrons have been injected into the base. Okay, and it will recombine with the holes in the emitter region. It will recombine with the holes in the emitter region. And holes have been injected into the emitter, right? Emitter, and it will recombine with the electron in the base. And since you see the concentration gradient, right, the holes also have been injected in from the collector here. Okay, so all will be recombined with the electron. The electron will be supplied by the base. Okay, so also this base will supply electron that to injected into the collector. Okay, and in the collector, the holes will be supplied from the contact for this injection also will recombine with the electron. Right. So let me summarize again. See, here the electrons will be injected into the base and it will recombine with the holes that is supplied from the contact. Again, the holes will be injected from emitter to base, and some of them will be recombined with the base electron. Right. Again, the electron will be injected because it is followed base from base to emitter. Some of them will be recombined with the holes, and the collector will inject the holes because it is equally followed base from base to collector to base, and that will again recombine with the electron. Okay, so since this is the condition, okay, so this is the real picture of the current flow when V is equal to 0, right? So, but you know, since the recombination in this base region is very, very small, right? Extremely small, right? I can neglect this current. This can be neglected, okay? And you see, since the slope here is very, very small, right? Generally, the slope should be like this, right? Should be like this, but it's very, very small. So this also can be neglected now. It's a simple approximation, okay? It can be neglected. And since this current is very, very small, right or not? Because this current is very, very small compared to this and this, the concentration is very, very small. This also can be neglected. They are there, but they are very, very small. They can be neglected. Okay? And since I said this is because of this concentration gradient, which is very, very small, this also can be neglected. Okay. So now what do we have? What we are having? So this is the IB. This is your IC. Okay. Here you can see in the simplified diagram, in this condition, IC is approximately equal to minus IB. Right? This will be the condition for V is equal to 0. So for V is equal to 0, you see, in reality, it is not 0. Okay. The IC is equal to minus I. This is your IB. Right? This is the condition for V is equal to 0. But this, since this IB in very, very microampere, then this voltage, okay, IB is very microampere, so it can be very negligible, right? So, but at V is equal to 0, the IC is approximately equal to minus IB. Okay. Now, what the condition now? Now, if you go on increasing the VEC, right? So VEC will be greater than 0. Then at some point it will reach a point where IC is equal to 0. Okay. So let us see how this happens. VEC is greater than 0. Okay. So now what will happen? A point will come where my IC will be equal to 0 here. How this will take place? Okay, we'll see. Now, VEC is nothing but VEB minus VCB is greater than 0. That implies the emitter bijunction is more forward bias compared to the collector bijunction, right? So very straightforward. You can plot the equation again. You can plot the concentration profile again. Okay, you see, since emitter bijunction is more, so this will be remain same much. Okay, here the injection will be takes place from here to here. Okay, so since BCB is small, so it can be little smaller. Okay, now you see at this junction, it depend upon the VEB. At this junction, it depend upon VCB. So here it is very less. Here it is very, very more. Okay. So if you plot the concentration, it will be like this. Okay. This will be the condition when VEB is greater than 0. Okay. This is your N, P, PNP. Okay. This is the concentration of holes, concentration of electrons. This is the concentration of electrons. Right. So this is the condition you see, because the junction here, this value depend upon the VEB. This value depend upon VCB. Since VCB is less than VEB, so you will expect a profile like this. Okay. So since you expect a profile like this, now how the current will flow now? Very clear now. You see, holes will be injected from emitter to base, right? And some of it will recombine with the holes, electrons. Recombine. Okay. Also, the electrons will be injected from base to emitter. So it will emit emitter. So it will recombine with the holes. Okay. And since the concentration gradient is very, very there now, earlier the concentration gradient was 0, right? Almost negative. Here, this is a concentration gradient. So, holes will be injected into the collector region, right? Also, the electrons have been injected from base to emitter because it is forward bias, right? So, the electrons will be injected from base to emitter like this, right? So, electron and hole will recombine now. Okay, this is the current flow, right, in BCB greater than 0. Okay, what is the change now? Now the current here is not negligible. So I can neglect the recombination current here. This can be neglected. Okay, can be neglected. Now you see there is a concentration gradient. So the holes are moving from base to emitter like this, and since BCB is greater than 0, right, and this is also injection from the base to emitter. Okay, this is base, this is collector. Okay, so because of concentration gradient, the holes have been injected from base to collector, and because it is forward bias, so the electrons also injected from base to collector. Okay, so you can see the hole and electron are moving in the same direction. Okay, so a point will come, right? If you go on increasing the emitter to collector junction, okay, what is happening? The hole and electrons are moving in the same direction. A point will come where the electron current, the current due to electron will be equal to current due to hole. Nothing but number of holes. So when you go on increasing the VEC, what will happen? VCB will go on reducing, VEB will go on increasing. And what will happen? A point will come, right, when number of holes moving is equal to number of electron moving. So at this junction, what will happen? The current will be 0. So when you go on increasing the forward bias, a point will come where the number of electron will be equal to number of holes moving in the junction. At this junction, what will happen? The current will be 0. So this is this point. Okay. Now if you increase again, now if you go on again increasing, so again VEC will be increasing. Go on increasing. What will happen? VEC will increasing means VEB is reducing, VEB is increasing, because VEC is nothing but VEB minus VCB. It is increasing means this is reducing, this is increasing. So what will happen? So in second case, suppose this is second case, I am marking in red. What will happen? This will be like this. Okay, and this will be like this. So the concentration gradient here is getting more and more. So the number of holes crossing will be more and more. So it will be increasing. Since the number of holes is more compared to number of electrons. Okay, so the current will be flowing like this. Okay, so the current will start go on increasing, because you see when I go on increasing the VEC, nothing but I am decreasing VCB and increasing VEB. Okay, what is happening? The slope of the carrier in the base region is increasing. So the injection from here to here is increasing, and since VCB is decreasing, this is also decreasing. So in second case, it will be like this. Okay, so this current is decreasing, this current is increasing. So whole injection is increased because the concentration gradient is more, so the whole injection is increased. Since the VCB is reduced, the value here is reducing, so this electron current is decreasing. So since whole is increasing, electron is decreasing, net current is electron, whole minus electron will be increasing. So if you go on increasing, what will happen? It will go on increasing like this, right? Then we will reach a point, okay? What will happen? When VCB will be 0, right? So if it is go on reducing, right, then VCB will equal to 0. A point will come where VCB is equal to 0. Equal to 0. Okay. So a point will come where VCB is equal to 0. Because the go on reducing, a point will come when VCB is equal to 0. Okay. So at this point, what will happen? We know. So if you plot the carrier concentration, right, when VCB is equal to 0, there is no injection from base to emitter. Okay. So and emitter base junction is forward bias. EB is forward bias, so file will be like this injection. Okay, so now here what is the carrier now? If you plot, okay, so this is the injection of electron from base to emitter. There will be injection of holes from emitter to base. There will be some recombination here. Okay, so I am ignoring the recombination current here now. I am ignoring the recombination current. Then what will happen? Because the concentration gradient is very more, so holes will be moving like this. So the holes because will be moving to the collector junction, ignoring the recombination current in the because base is very thin, right? Base is very thin, so I can ignore the recombination current. Okay, so when BCB is equal to 0, because the slope is more, I'll get collector current. Okay, you get collector current. What will happen? My BCB again decrease means BCB will go to negative, right? BCB will go to negative. So when BCB is equal to 0, I will reach this point. This is the point where BCB is equal to 0. So at this point, okay, my BCB is equal to 0 at this point. Okay, at this point, BCB equal to 0, VC is equal to there, VB is equal to there. Okay, so I at this point this one. And then again, if I go like this, what will happen when I increase more VC means BCB is negative now. So become 0 now. Now if I decrease BCB negative, if negative, what will happen? This junction will move towards, when BCB negative, what will happen? This junction will move towards this one. So this is for BCB equal to negative. Okay, so move forward. So then this also will move forward. If I plot the concentration, it will be like this. So the slope will be increasing. Slope is increasing. Okay, so when BCB is negative, right? Like in this region, right? In this region BCB is negative or BCB is reverse bias. What is happening? Since the slope is increasing, okay, if I increase more, what will happen? The junction will be coming like this. And what will be slope? The slope is increasing. Since slope is increasing, there will be a slight increase in current. When BCB is negative, BCB is negative. Since the slope of the carrier is increasing, because base width is sinking, okay, there will be a rise in current. Okay, there will be a little rise in current. This is due to nothing but base width modulation, which already we explained. Okay, so current will go on increasing. At this point, BCB is equal to 0. So in this point, what will happen? BCB and VEB. So in this region, both BCB and VEB both forward bias. In this region, BCB reverse bias, VEB forward bias. Okay, there is nothing but saturation region. In saturation region, the current is approximately constant. Only there is a slight increase in current because of your base width modulation. Okay, base width modulation, there is a change in current, very small. Okay, so this region is very useful, right? So this region is called saturation region. This region is called active region. So this active region is very extremely useful for amplification purpose. Okay, the saturation region is useful for switching purposes, but for amplification purposes, this active region is very useful. Okay, so that will be discussed in detail in analog circuit part. Okay, so because you see in this active region, right, the transconductance GM is very high. GM is high, and the output resistance RO also high. So since GM and RO is giving you your amplification factor, so the amplification also will be more in saturation region. In this region, the RO is very less, GM also is very less. Okay? Here GM and RO both are less in this region. So it is not useful as a amplification factor because in this region, the transistor action is not taking place. Okay, transistor action is nothing but transfer of current from a forward bias junction to a zero bias or reverse bias junction. So this is takes place only in this region. So since the transfer of current from forward bias junction to reverse bias or zero bias junction taking place only in this region, that's why it is called active region. And in active region we will get amplification. In this region, both are forward bias. The proper transistor action is not taking place. Okay, so I hope you understood how. And thing is, the BEC where the IC is only 0 is in very millivolt. In millivolt, this current is in microampere. Okay, so if you see, most of the curve will be like this only. Okay, IC BEC characteristic for a particular IB is like this. But if you zoom in this one, you will get this one. This is in microampere, this is in millivolt. So most of the books you can see this is starting from 0, because this is micro and millivolt looks like few millivolt, few microampere. So looks like starting from 0 only, but in reality it happens like this. Okay, so this is my current voltage characteristic. Okay, so with this I want to conclude this BJT chapter. Okay, so where you have understood very lot of things you have seen in BJT. So we have seen in BJT the construction. Also we have seen how the current transfer from emitter bias junction to collector bias junction using this thought experiment. Then we have seen what are the basic factors of transistor. One is emitter injection efficiency, another is base transfer factor. Okay, so we have understood for a proper transistor action, the emitter doping is very more compared to base doping, and the base width is very less compared to diffusion length of the base. Okay, then we have seen there is something called alpha is current gain. Okay, IC by IE. Then beta also we have seen. Then we have seen the effect of collector bias. So if the collector bias is forward bias, we have seen how it is destroying your transistor action. When it is reverse bias, it is helpful for your transistor action. Okay, so in reverse bias and forward bias, both things we have seen. Then we have seen small signal analysis, like we change the emitter bias junction with a little small amount, and how the collector current is changing. Okay, this we have seen. The collector current is changing linearly if VB is very less. Okay, then we have seen how the amplification takes place. Then we have seen base width modulation. Then we derived a expression for emitter current gain alpha in order to appreciate why with base width modulation the current gain is increasing. Okay, then we have seen the configuration called common emitter configuration. So in common emitter configuration, the input current is IB. So we have derived expression for the output current, collector current. Then we have seen how the IC versus VC characteristic is coming. Okay, so we've seen in detail each and every point of this characteristic. Okay, this is for one IB. For different IB, this will be different, like we have seen here. Okay, this is my output characteristic. So with this understanding, so we can easily solve questions in analog circuits, and if some questions come in device physics. Okay, so this is giving you a in detail physics of BJT, and by this understanding, it will be good to solve the questions from analog circuits also. Okay, so by this I am completing the BJT chapter. There are a few other things also. For the time constraint, we will be limiting to this one. Okay, so wish you all the best. Have a great exam.